Hello everyone, welcome back. In the previous videos, we understood about binary search tree and different types of balanced binary search trees like A-Bull tree and red-black tree. In this video, we will understand the different balanced trees like B tree and B plus tree in a detail. Before going into the details of B tree and B plus tree, let's take one problem and see how B tree and B plus tree help to solve that problem so that we can understand the use case of B3 and B plus tree in a much better way. So let's start. Let's say we have a database, or now think of it as a SQL database, where we are storing the users table. So it contains user ID, email, name, age, address, all this information about the user. And let's say we have 1 million entries into the table. Now, the table on a database is actually stored on a disk. So the table is stored as a file on a disk, right? You might have seen the database files. So basically, that is nothing but the table which is stored as a file on a disk. Now, to be able to store and retrieve the information from disk easily, the disk is represented little bit different. So basically, the disk is divided into tracks. Right? So this is one track, this is second track, and so on. Right? And these tracks are then further divided into sectors. Right? So these sections, which you can see, are called as a sector. For now, we can think of sector size as a 4 KB to basically understand this example easily. And in this sector, the data is stored as a logical file block, right? So this whole table is a big and file. Basically, that file logical file blocks are basically stored as a data on this sectors. For now, let's consider the size of that logical file block as 4K. It means that that block will store the 4 KB of data. So whenever we say give me, let's say one end row, let's say Adam with email Adam at the rate example.com. So basically, internally, it basically goes to the specific sector and track. That logical file block is converted into the physical sector and track so that disk spindle can spin the disk and the head will basically go to that particular sector and track section and retrieve the logical file block to give the actual data. So this is how the disk IO works. Now, how this table will be represented on a disk. So let's say each row of this table have a size 256 bytes. Let's add some. Now, what will be the total table size? So 256 into 1 million. 1 million rows are there. So it is 256 million bytes, which is approximately 244 MB. Now, to store this 244 MB data, how many number of logical file blocks will be needed? As we consider 4 KB as a logical file block size. So 256,000 KB divided by 4, it will take 64,000 blocks to store this whole table. And each block holding approximately 16 rows, right? So 64 blocks are basically stored on this disk, logical file blocks, which are representing this whole table with 1 million entries. Now, whenever we do basically some query on this table, like select star from users, where email equal to alex@example.com, it will have to go and parse all the 64,000 blocks, right? And go to the particular block. And whenever it sees that, okay, for that particular block, in that 16 rows, whenever it sees the row with the alex@example.com, it will return that row. Now, passing the 64,000 blocks, the disk IO is expensive. Right? So this is not basically, it will be like very expensive operation. And if there are too many queries, then it will not work properly. So to solve this problem, now here we are basically storing the data, and whenever we are querying, we are directly going to that 64,000 blocks. So rather than directly going and checking all the 64,000 blocks, how can we optimize this further? So the concept called indexing comes into the picture here. Now this is our data table. So on the top of this data table, one index table is created, which is basically the small table. It contains like kind of a key and the logical pointer to sector and track, right, where this actual row is present. Right? So it contains the pointer to that sector and track. Now we created the index table on top of this actual data table, right? So this is called as an indexing. Let's say one row of this index table is 32 bytes. So now whole index table can be stored into the 8,000 logical blocks. If we say 4 KB as a one logical file block size. So whenever we do the query now, right? Now let's say we are doing select star from users where same query which we saw in the previous slide. So now how we optimized it? Basically, rather than going for checking the 64,000 blocks, it will first go and check the 8,000 blocks. And in that 8,000 blocks, it will check for the key where this is the key, alex@example.com, and then face the pointer to the exact block, logical file block pointer for where that row is present, actual data is present. So that way, we are actually parsing only 8,000 plus one block, which is 8,001 block, compared to 64,000 blocks which we are passing. So without indexing, we had to traverse 64,000 blocks. But now with indexing, we are parsing this 8,000 blocks first, and then directly one block only, because we have a pointer for that block, data block. So 8,000 plus 1, 8,001 blocks. So with just one indexing, we actually optimized by 8 times, right? Our read became fast. So now each block here in this 8,000 blocks, each block is containing 125 rows. That's why we are requiring only 8,000 blocks. Here it was storing only 16 rows, right? So that's why it was 64,000. Now we reduced our traversing from 64,000 blocks to approximately 8,000 blocks, but it is still not optimized, right? Because parsing the 8,000 blocks is still very expensive considering the disk IO. Right? So how can we optimize further? So let's say this is our index table, right? So this index table requires 8,000 blocks, right? So to represent it, basically, let's say this is our index table, which is index entries, 1 million index entries. It required 8,000 blocks. So each block will have approximately 125 rows. And what is containing? Email and data point. Here is email and data point. So we can think of block 1, block 178, etc., till block 8,000. Now, can we create index on top of this index? See, we created this index table on top of actual data table so that we don't need to pass the 64,000 blocks, right? So can we create index on top of this index table so that we don't need to pass 8,000 blocks again? So let's say we created one more table where it will contain basically, let's say it is containing more keys rather than just single key like this, contains more keys and basically block pointer for each key, basically key pointer pair. So let's say this is one block and like this, let's say we have created 52 blocks, right? So if you want to represent it much better way, we can see that part also. So basically we are saying, okay, this block one is containing the keys and pointer for this block 1 to block 150. Right? So basically, this 150 blocks are now reduced to one block, right? Mapped to one block because we are getting the pointer here. Similarly, whatever it is, like 7,000 last block, 7,850 to 8,000. But to represent it in a better way, let's say we have this 52 blocks like this. So block 1, 2, 3, dot, 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 block 52. So we created this index table on top of this index. Okay? And then based on, let's say, Adam@example.com, this is a key. So that key may, similarly, there are keys still Alex@example.com. So, and based on the keys values, it is pointing to that specific blocks, right? Now, in indexing, the keys are always sorted. Right? So based on that, it will check the keys and go to the specific block because by checking the key value and because the blocks are sorted, index blocks are sorted, it can go directly to the specific blocks. Right? We have a key and block pointer pair here. Now we created this index on top of this index. We can create one more index on top of this index. Okay? So let's say it has, let's say, any at the rate example till zi at the rate example. It will point like this. So how will the select query work in this case? So let's say select star from users where email alex@example.com. So it will come here first. Okay, Alex AD. So it is basically greater than AD. So it is starting with AL, but it is less than AM. Right? So it is basically it will come to this first block. Okay? And then from here, so the Adam@example, and then it might be pointing from block 1 to let's say 10. And then we are going to Alex@example. Okay. It might be pointing to 132 block 150, something like that. So it will directly come to that 20, basically the 15 blocks. Right? So one block, two block, and 15 block, and then basically going to the actual data pointer. Right? So we can see from 8,000 blocks, we actually reduced the block traversal much less. Basically, we are just traversing few blocks. So because of this index on top of index strategy, we are able to basically reduce the block traversal very, very fast, right? Or very drastically. What is this called then? This is called as a multi-level index. Okay? So initially we created the indexing on top of actual data. So this is index table where each entry contains, basically there is an index entry for each key, each email. And then we created index on top of that index because traversing the 8,000 blocks is still very expensive. Right? So we created index on top of that index so that we can group the blocks and map it to just one single block here. And further, we created one more index here, which is mapping to all these 52 blocks. So this is called as a multi-level index. Now, if we observe one thing, if let's say we consider this block as a node, then we can see that it is looking like a tree structure. So to be able to maintain the indexing efficiently, whenever the new keys are added or new values are added to the database or values are removed from the database, this tree-like structure helps to keep that indexing balanced and efficient. Okay? So we can see that in a multi-level indexing, the tree-like data structure is used, and that is why the B tree and B plus tree comes into the picture. Okay? This is nothing but the B tree and or B plus tree. Okay? Now, before understanding the B tree and B plus tree, let's understand the structure here first. Right? So you can see, let's say if we consider this one block as a node, and then this multiple keys, So each block or each node is storing multiple keys. Right? So this is a different type of node structure. So let's understand what does it represent. Right? So we know that in a binary search tree, each node stores one key, right? And stores with two children, left and right. In an M-way search tree, it basically stores M children because it is here two children. That's why it is called as a binary. So here it stores the M children. That's why it is called as an M-way search tree and M minus one keys like this. As we saw in the previous slide, the indexes or the keys are stored in a sorted order. Right? That is why it is called as a search tree. Right? Similar to BST, it is M-based search tree. M is number of children. Let's say M is 4, so it contains 4 children, and N minus 1, 3 keys. Right? And basically, the first children is basically the keys which are less than the 20. Second children is keys which are greater than or equal to the key 1 and less than key 2. Third child pointer is basically key is greater than or equal to the second key and less than third key. And the last children is basically all the keys which is greater than or equal to last key. So this is called as an n-way search tree. Okay. To understand the structure in a more detail, let's say this is a node structure where K1, K2, K3 are keys in a node, and these are the child pointers. So this leftmost child pointer is the pointer to children which are less than K1. This is the pointer to children which are greater than or equal to K1 and less than K2. This is greater than or equal to K2 and less than K3. And this is pointer to children which are greater than or equal to K3. So this is M minus 1 keys and this is M children's. So M is a 4 here. So this is how the node structure in M-way search tree looks. So these keys are also sorted in a order. Now this is the M-way search tree, right? But there is a problem with the M-way search tree similar to binary search tree. Let's understand what is the problem and how the B tree and B plus tree help to solve that problem and works in an indexing problem. So let's say we take the example insert 10, 20, 30, 40 till 100 in this order in an M-way search tree. So let's say M is a 4 so that each node can have n minus 1, 3 keys and n equal to 4 children. So let's say we added 10, 20, 30, fine. Now when we want to add 40, this node is full, contains n minus 1, 3 keys, right? So it will create a new node and where it will add? It will add as a right child of 30. So it added 40, 50, 60. And similarly, when we try to add 70, 80, 90, it will create the right child, add those values, and last 100 is added. Now, if we observe this carefully, this M-way search tree is basically unbalanced M-way search tree, similar to the binary search tree, like right side skewed. It is similar to the balancing problem which we see in a binary search tree. The same balancing problem comes in a M-way search tree also. Right? Now, to solve this unbalanced M-way search tree, the B tree and B plus tree comes into the picture. Till now, we understood how the indexing works, how the multi-level indexing works, and how the multi-level indexing is actually represented as a tree-like structure. And we know that in a multi-level indexing, B tree and B plus tree basically are used. But before actually coming to the B plus tree and B tree, we understood what is M-way search tree and what is the problem with M-way search tree unbalanced problem, similar to binary search tree. Now we'll understand how that is solved using B tree and B plus tree so that it works very efficiently with the multi-level indexing in a database. So let's say we insert the same values in the same order in a B tree first. Right? So there are certain rules to follow whenever we are constructing the B tree. So this first two rules is basically the minimum keys per non-root node should be m divided by 2 minus 1, which is 4 divided by 2, 1. Minimum children per non-root node, which should be m divided by 2. Because it will be always 1 greater than keys, right? That's why it is m divided by 2. It's minus 1 plus 1, which is m divided by 2. Why these rules? So that we know that in a m-based search tree, now B tree is nothing but the balanced m-based search tree, right? So in an m-based search tree, uh, there are multiple keys present in a root. Basically, m minus 1 keys are present in a root. So to be able to utilize those key slots or the spaces available, we need to make sure that we are filling that node first before actually creating a new node. That's why these two rules are there to utilize the space. The next rule is new key is always inserted at a leaf node. So initially it is always inserted at a leaf node. When node becomes full, let's say we are constructing the binary tree and now we are adding a new key to the node which already have m minus 1 keys. So let's say when node becomes full, what we do? We find a middle key or median key in a node, right? Promote the median or middle key to the parent node, and that current node, split that current node into two halves. So left child contains the keys less than median or middle key, and right child contains keys greater than median or middle key. We'll understand this with the example. Right? Now, when we promote this middle key or median to the parent node, let's say parent also is full, right? So we need to recursively follow this split step and promote to the upper limit. All the leaf nodes are at the same level. This property or this rule is automatically covered using this. So we'll understand how it automatically happens, but all the leaf nodes are at the same level in a B tree. Now let's take the same example. Let's say we added 10, 20, 30. Now when we add 40, there is no space, right? So 10, 20, 30, 40. What we do, we find the middle key. What is the middle key of 10, 20, 30, 40? This 20, right? So basically what we do then, we promote the middle key to the parent. Now there is no parent. So we create a new root and add 20 there, promote 20 there. And the left child basically key is less than 20 and right child is key is greater than 20. So this is how we split the node. Fine. Now we'll add 50. And then when we try to add 60 here, it is already full, right? Why we are not adding here? Because new keys are always inserted at a leaf node. So that leaf node will always be at the same. So it will come here. We will try to add 60, 30, 40, 50, 60. What is the median? It is 40. So it will promote the 40 up, divide that node, basically the previous node, divide the 30 to the left child of 40 and 50, 60 as the right child of 40. Now let's say we added 70. Now we are trying to add 80 here. It is again full 50, 60, 70, 80. What is median? It is 60. So we'll promote the 60 up and divide this node into two halves. 50 will be the left child of 60 and 70, 80 will be right child of 60. Like this. Now we are adding 90. We added. Now we want to add 100. So when you add 100, now the keys are full. Basically the node is full here. Now we are adding 100 here. So what we do 70, 80, 90, 100. Now we take the median, which is 80. 80 will be promoted. Now this node will be split into two halves. 70 will be the left child of 80. 90 and 100 will be right child of 80. Now when 80 goes here, this is also full, right? So that will also get split up. 20, 40, 60 and 80. What is the median? median is 40. So it will be split, 40 will be promoted and new root will be created. And 20 will become the left child of 40 and 60 and 80 will become the right child of 40. So it will look like this. So we can see the structure of the tree is balanced compared to what we see in a just M-way search tree. So this is a balanced M-way search tree, which is B tree. So one thing to note with the B tree is that as we saw in a example, the email example or the table example which we saw, the last row basically it was containing the email key and actual data pointing, right, to the actual data block. In a B tree, whenever we split the node, right, previously it was 10, basically it was 10, 20, 30, right, and when 40 came, we split it. So 40 went, 20 went out here. So when we split the node, the actual data pointer also goes here, right? So that is the one thing we need to keep in mind when we will see the B plus tree. So whenever we split the node, the keys and the actual data pointer moves to the internal node, right? Whenever we are splitting the node and promoting that median or middle key. But in a B plus tree, what happens is the same numbers when we insert in a B plus tree, it will be represented like this. Now, one thing you can observe that all the values are present at a leaf node and we can see duplicates here. But in a B plus tree, the internal nodes only contain the key, right? It does not contain the actual data pointer to the rows. It will be present here only. So why we are at the reason we are storing here only because at a leaf in a B plus tree, the leaf nodes are connected to each other. Right? So it becomes easy to traverse when the data pointer is present here. And it also helps in a range queries. Let's say we want to find the elements between 20 to 60. In a B tree, what will happen? You will come here, you will 20, you will get the data here, come back again, then go here and then go and find the keys which are basically less than 60. Right? But in a B plus tree, we can easily basically come here, you got the 20, just keep traversing because it is like a connected like a chain. You keep traversing till 60 and you got it. You don't need to traverse again up and down. Okay? So that is the benefit of B plus tree in a sequential or range queries. And because the internal nodes contains only keys for routing purpose, it does not contain the data pointer. The data pointers are stored at the leaf level only. So it becomes easy to traverse during the chain and fetch the actual data. So that's why we can see duplicates here, but it is not actually duplicate. It is the only key is copied here so that it can help with the routing purpose. So that is the difference between B tree and B plus tree. B plus tree is nothing but the next or updated version of B tree. It follows the same rules. Only thing is that actual data is stored at the leaf node only. And whenever we split the node, only key is moved up so that it can use it for indexing and routing. So this was a B tree and B plus tree, we understood. So to summarize, what are the difference between B tree and B plus tree, right? The actual data in a B tree is, you can find it at any node, internal or leaf, because when we split, the actual data also or pointer also moves to the internal. In a B plus tree, you will find it only in a leaf node. So internal node, as mentioned in first point, in a B plus tree, it only contains the keys for routing purpose and pointers to children. In a B tree, it stores the keys and also data pointer, actual data pointer, and uh, child pointers. Leaf nodes are connected in a B plus tree. They are not connected in a B tree. Search performance, it might be slightly better in a B tree because you might get the data in internal node only. In a B plus tree, you know that you will get the data at leaf node. So always you will go to leaf node and find data. So it is consistent. Okay? As explained in previous slide, the range queries are less efficient in a B tree because you have to come to one leaf and then traverse up again and check for the another keys. Like let's say you want to find data between 20 and 60, you come and find for 20 first and then go for 60. Okay. Now B plus tree, it is highly efficient because the leaf nodes are connected. So if you find the first key, you can traverse the leaf nodes as a linked list. Key duplication in a B tree, keys are not duplicated. In a B plus tree, keys are duplicated because when we split, we are just copying the keys home. Because of the benefits of B plus tree, and it is just the updated version of B tree, B plus trees are most commonly used in a database indexes. Okay. So we saw how the B tree and B plus tree are useful for indexing purpose. Right? Now, if you think this previous example, think of this node as a email keys only. And this is basically the email index table, which we saw in the previous example. How it becomes easy to come to the particular index and then fetch the actual data from the disk. Okay. And because the B tree and B plus tree provides the balanced structure, so the search and basically the database operations becomes very, very efficient. Okay. Now, one question might come, why we are not using other type of balanced trees, because the red, black tree, alien tree are also uh, balanced trees only. Why they are not used in a database indexing? The reason is, in a B plus tree, you can have multiple children for each node, right? Multiple keys and multiple children. In a AVL and red, black tree, it is a binary search tree, balanced binary search tree. So you can see that it will require more space, right? And you will end up passing more blocks and you will not get that benefit. Right? In a B plus tree, it is because you are able to store more keys and more children, you get too much big range within small height of tree itself. You don't get that in a binary search tree. Right? That is the reason. And one question might also come, why not arrays or hash is used in indexing? Valid question. But if you see in a B tree or B plus tree, the indexes are sorted in order, right? So for a ordered queries or let's say range queries, you will not get that benefit in a hash, right? So that benefit we get in a B plus tree or tree-like structure. And the problem with arrays is that whenever we delete the element, you will have to shift the elements, resize the array, all those things, right? In a tree-like structure, whenever you delete anything, it gets adjusted and balanced very efficiently. Okay? So considering all these factors and trade-offs, that is why B tree and B plus tree came into picture to solve the problems like indexing, right? Whether it is database indexing, file indexing, etc. So hope you understood about the B tree and B plus tree in a detail and how it helps to solve the real life problems like database indexing, right? What is M-based search tree? What are the problems with it and how B tree and B plus tree solves? What is the difference between B tree and B plus tree? And why other data structures like balanced binary search tree, array, hashes cannot be used to solve such cases, and why B tree and B plus tree are only suitable for solving such cases. So if you like the video, please share and subscribe. Thank you so much.